5.5. So we start out today, we are factoring, but now factoring polynomials. So we are still using the methods of factoring that we used in Chapter 4 with quadratics, and now applying them to all polynomials. We still will see quadratics in this section. Quadratics are polynomials, so we'll wrap up and use those methods as well. The first set of examples, though, are just focusing on using two new special methods of factoring when you have sums or differences of two perfect cubes. So you may remember, and it's actually on your sheet, you have to look down towards the bottom in that factoring techniques box. You may remember factoring a difference of squares, a difference of perfect squares. So when you have something of the form a squared minus b squared, it factored to a plus b times a minus b. So sums or differences of two perfect cubes. It's a similar idea. You don't have to memorize either of these, but you have to know how to use them. So memorizing, you do not have to memorize that. So first of all, a perfect cube. Just like a perfect square is when you take a number squared, so like 16 is a perfect square, square root is 4. Perfect cube, same idea, but you're looking for what number cubed equals that number. And there is a way to find cube roots on your calculators, which I'll go through, but then if you have questions on the calculator you're using, let me know. So I just want to point out these are very similar. What's different between them is whether or not you have a sum or a difference. So when you have a sum of two perfect cubes, so it's in the form a cubed plus b cubed, this is the factored form, so this is what you would be finding. In this form, though, a is the cube root of whatever a cubed is, so the cube root of your first term, so like a square root, but you're finding what cubed would equal that quantity. And then b is the cube root of b cubed. So I know you saw this in Algebra 1. I know that was a while ago. So a cube root or a fourth root or a fifth root, you still make that radical or square root sign, but the index is whatever root you're looking for. So if it's a cube root, you want the index to be 3. A square root does have an invisible index of 2. They don't write the 2 in there. So it would factor to be a plus b, your two cube roots, times, and then a squared minus a times b plus b squared. Notice, well, I'll point this out after I talk about the second one. So then for the second one, if it's a difference, you're still finding the cube root of both terms, but then it's a minus b times a squared plus ab plus b squared. So even though I'm giving these to you, I want to point out the main difference between the formulas. Each formula has one subtraction sign, and the difference is where it is. In a sum of two cubes, the subtraction sign is the AB term is negative. In a difference of cubes, in the first factor, the A minus B, that's minus versus plus. So each formula only has one minus sign, the rest are plus, but again, you don't have to have that memorized anyway. I'm giving it to you, you just have to know how to find A and B and then substitute them into the formula correctly. And then, not necessarily that this applies to these three examples, but an idea that we have talked about, if you cannot factor a polynomial, it is considered prime. So on the practice you have for this lesson on the homework, there will be some that are prime. We will see some that are prime in our examples. So that's just in general, not just for these three. Anytime that you can't factor something, it's prime. So the directions you're going to see for any of these, it's not going to tell you what method to use. You have to determine that, but it just says factor each polynomial. If the polynomial cannot be factored, write prime. So if you look at A, and these three are practicing these two methods, sums and differences of cubes, since they're new. So if we look at A, we have two terms. First of all, whenever you factor, we've talked about this before, what do you look for first? whenever you factor. GCF, that still applies. So n cubed and 125, do they have anything in common besides 1? I see some no's. Okay, so that I'm just pointing that out. You should always look for that first. So then, if you only have 2 terms and they're being subtracted, since I know I'm using either of these methods, I should check to see, do I have a difference of perfect cubes? So are both terms perfect cubes? Now, when you have exponents on a variable, it is a perfect cube when you can divide it by 3, or when it is 3 itself. So n to the 3rd power is a perfect cube. N to the 6th power would be a perfect cube. N to the 9th would be a perfect cube. So anytime you can divide the exponent by 3, it's a perfect cube. So I know this is a perfect cube. The cube root would just be n. And then is 125 a perfect cube? Is there a number cubed that would equal 125? Does anybody know? 5 cubed. I will show you how to find that on your calculator. So I'm going to show it on if you have one like mine. Now I realize you don't all have one like mine. So when you have a chance, I'm going to have you do example 3 on your own when you're working on that and I'm walking around. If you have a different calculator and don't know how to find a cube root, let me know and I will help you figure that out. On this calculator though, if you're not sure how to do it, just like anytime you want to take the square root of something, you have to hit second and then x squared to get the square root. The caret key that you use to raise any number to any other power besides 2, if you hit second and then the caret key, that allows you to take any other root, like a cube root or a 4th root. What you have to do on this type of calculator, though, is type in the index first. So if I want a cube root, I need to type in 3 first. And then I would type in second and the caret key. And this is what you want to come up. You want that x root to come up because then it'll replace the x with the 3. And then you would type in this case, 125. And it'll take the cube root of 125 and tell you it's 5. Okay, so I know that was quick. I know you don't all have this calculator. So again, when you're working on example C and I'm walking around, if you have questions on your calculator, let me know. I will help you out. So once you find the cube roots, so I have a difference of perfect cubes. Since they're being subtracted, I want to use that second formula that's in the box above. N is like the A in the formula, 5 is like the B. So the factored form following this formula is going to be, it starts out with a minus b, so that's going to be n minus 5, times a squared, so that's n squared, plus a times b, so that's n times 5, or I can write that as 5n, plus b squared, and b is 5, so 5 squared is 25. And this is the factored form. Okay, so you have to identify it's a sum or difference of cubes, find the perfect or find the cube roots, and then just use the correct formula. Don't have to memorize it, you need to know how to use it. Questions on A? All right, if we look at B, 24x to the 5th plus 3x squared y cubed. So hopefully you can tell just from glancing at the exponents, as it is right now, we don't have a sum of cubes. Is there a GCF for these two terms? They have a 3 in common. Anything else? An x squared. They both have an x squared. So I should factor out the GCF first. So remember, when you factor out a GCF, you're dividing both terms by 3x squared in this case. The GCF gets written in front of parentheses. What's left goes inside. So when I divide them both by 3x squared, I will get 8x, and then I subtract these exponents, so 8x cubed plus And then I would just be left with y cubed for the second term. Okay, so now that I've taken out the GCF, I should still check. I'm just going to ignore the GCF for right now. I should still check, though, inside the parentheses, can I factor that more? So I have a sum of two terms. So my clue is to see, since it's a sum, are both terms perfect cubes? I know x cubed and y cubed are. Is 8 a perfect cube? Is there a number cubed that equals 8? 2 does. So the cube root of 8x cubed is 2x. The cube root of y cubed is just y. And again, I'm just ignoring my GCF for right now. It'll be part of my answer, but I don't need it at this moment. So I'm using the sum of cubes formula. 2x is like my A, y is my B. So I have A plus B, so 2x plus y, times, now when you see a squared here, since a is 2x, that means I really have the quantity 2x squared. So I'm going to be writing this differently in my final answer. I have to square the 2 and the x, so it's really going to be 4x squared. And then I have minus a times b, so that's 2x times y, or 2xy, plus b squared, so plus y squared. Okay, so I will put the GCF in front, but I'm going to rewrite this, rewriting the 2x quantity squared as 4x squared. So final answer is going to be 3x squared times 2x plus y times 4x squared minus 2xy plus y squared. Okay, questions on that one? All right, so then I want you to try part C on your own or in your groups, factor that polynomial. And then again, when I'm walking around, if you have questions on using your calculator to find a cube root, let me know. I can help you with that while I'm walking around. Everything is fine. You actually have any other root though, like if actually Okay, double check what you have in case I didn't exactly look at yours if you were still working. I know some groups I just checked one person's. Hopefully you're checking with each other, helping each other out that way. So be careful. The formulas are very similar, and you are given the formulas. But I think the biggest mistake I noticed when I walked around were your signs. Make sure you're watching your addition and subtraction signs in the formulas. That would be my main thing. Otherwise, the terms are all the same. You just have to watch your signs. Okay, any questions before we move ahead? We are still going to be practicing these as we move forward, but we're using more methods as well. Okay, so then the bottom of this sheet, this is a very important box for you to reference when needed because it summarizes all of the techniques of factoring that you would need to use. Okay, so this is how it works. What it says at the top, the main thing I want to draw out of this is that whenever you're factoring, what I've always said is you always look for a greatest common factor first. And then what you want to do is determine, based on the number of terms your polynomial has, which method of factoring should you try. And then if it works, awesome. If it doesn't work, it's possible that the polynomial is prime and cannot be factored. So here's a quick summary. Any number of terms you have, factoring technique, you should always check for a GCF. Okay, and it does give an example of each case as well. After you look for a GCF, determine how many terms you have. If you only have 2, there are only 3 methods of factoring you could try. If none of them apply, it's prime. So here's the sum of 2 perfect cubes, the difference of 2 perfect cubes that we just talked about in the 3 examples above. Difference of squares, that was from chapter 4 that I referenced before. So if you have 2 terms but it's not a difference of squares or a sum or difference of cubes, it's prime. If you have 3 terms in the form ax squared plus bx plus c, it is a trinomial. You should factor using the diamond, or if you like to guess and check, using guess and check. Okay. Now there are perfect square trinomials. That's a very specific method for a specific type of trinomial, but you can still factor perfect square trinomials this way. Perfect square trinomials are the ones we factored by completing the square. And then if you have 4 or more terms, grouping is the method you should try. And again, if grouping doesn't work, it's prime. So this is what you should reference when you need to. That's why I copied it for you. You have it. But we will now go through more examples putting this together. So again, directions are the same. Factor each polynomial. If it can't be factored, write prime. So if we look at A, how many terms does A have? 4. What method of factoring should we try? Grouping. Okay, so I included one. This is going to be a review of grouping. We did this in Chapter 4. Grouping isn't new. So this is where you group the first two terms and the last two terms, and you find the GCF of each pair and factor it out. So the first two terms, what do they have in common? X squared. So I write the x squared, and in parentheses, I write what's left when I factor it out. So when I divide these both by x squared, I'm left with x plus 5. Okay? Then, last two terms, what do they have in common? And negative 2. So I'm going to write after this minus 2, and in parentheses, what's left when I divide by negative 2. So negative 2x divided by negative 2 is a positive x. Negative 10 divided by negative 2 is a positive 5. So x plus 5. Grouping only works if your parentheses are the same. If they're not, either you didn't correctly find the GCF or factor it out, or it's prime. So since these are the same, then remember to fully factor this. This isn't your answer. This means one factor is x plus 5. The other is x squared minus 2. Now, I have one additional thing to say, and that is when you're factoring, whenever you use one method to factor, you should check if you can still factor anything. So when I look at my two factors I have left, the first one, the exponent on the x is just a 1. So when your exponent on your variable is just 1, this is considered a linear factor. You can't factor that any further. That one is done. The second one, though, what sticks out to me is that it's an x squared. So when I have two terms, and the first one is an x squared, that's a perfect square, this could be a difference of squares. And if it is, I would have to factor it further. If it's not, I'm done. So since x squared is a perfect square, I would have to check, is 2 a perfect square? No. So this actually is fully factored. I'm just pointing that out so that when you are factoring, you notice things like this. If you see an x squared still in your polynomial, check to see, can I factor that more? Because if you can, and you left your answer this way, it wouldn't fully be factored. You wouldn't be done. Okay, so just things to look for. Example B. How many terms does example B have? 6 terms. What method should we try? Grouping. So 4 or more terms. Grouping is what you try first. When you use grouping, no matter how many terms you have, now grouping will only work if you have an even number of terms. Because when you group, you're only making 2 groups. So when you have 6 terms, you're making 2 groups of 3. So if I look at the first 3 terms, the way it's written, do the first 3 terms have anything in common? They have a 6x in common. Okay, so I'm going to factor out a 6x from the first 3 terms. When I factor out a 6x, I'm left with 5a minus 4b plus 1c, or just c. Okay, then the last 3 terms, do they have anything in common? Y squared. Would I want to factor out a positive or a negative y squared? What do you think? A negative. Now my clue is I want my parentheses to be the same. If I factored out a positive y squared, I would have a negative 5a, and it wouldn't be the same as positive 5a. So I do want to take out the negative. So that way I have a positive 5a, and then I would have a negative 4b and a positive c. Okay, so my parentheses again are the same. So grouping does work. I should finish this. One factor is 5a minus 4b plus c. The other is 6x minus y squared. And if I were to check, can I do anything else? My first factor has 3 terms, but all the variables are different. They're all powers of 1. That's factored. The second factor, my last term is a perfect square, but the 6x is not, so it's not a difference of squares. So this is finished. And the only way to really be able to recognize, hey, I could probably factor that again, practice. I know I stress the homework a lot, but that's how you start to recognize these things. Okay, questions on B with 6 terms. Okay, and then C and D are both similar. D, there's one additional thing that's different, so I actually want to skip ahead to D to make sure we get through our examples and leave some time for you at the end to work. If you look at D, D also has 6 terms. If you look at the first 3 terms, do they have anything in common besides 1? They don't have anything, not all 3. If you pair 2 of them together, you could take something out. But the way it's written, not all 3 of the first terms have anything in common. You could also check the last 3. They don't have really anything in common either, all 3 of them. Now, this doesn't mean it's prime. It doesn't mean grouping won't work. But what it does mean is you might have to rearrange your terms first. So if I look closely, when you're rearranging terms, focus on the variables, not necessarily the numbers or the coefficients, but focus on the variables. If I look at the variables closely, I see I have A's, B's, X's, Y's, and Z's. Okay? Now, 3 of those 6 terms have an A, 3 of them have a B. Those are going to be my 2 groups. I want my first 3 to have the A in common, my last 3 to have the B. So I see 13AX minus 14AZ plus 9AY. Those 3 have an A. And then I'll box the other ones. They all have a B. So I'm just going to rewrite this so all of my A terms are written first, all of my B terms are written last. So 13AX minus 14AZ plus 9AY. And then my B terms plus 18BZ minus 15BY minus 32BX. Okay, but then at least I know when I make my 2 groups, my first 3 at least have an A in common, my last 3 at least have a B, so I can try grouping. Now, the first 3, do they have anything besides the A in common? Is there anything else I could take out? I see some no's. Okay, so if I factor out an A from the first 3 the way I rewrote it, I'd have 13x minus 14z plus 9y. And then the last 3 I know have a B in common. Do they have anything else? So it looks like 3 because 18 and 15, but 3 does not go into 32. So it looks like there's just a B, and I'm just going to try taking out a positive B. If I need to change it to a negative, I can. When I factor out a B, I have 18z minus 15y minus 32x. Okay, so when you look at your parentheses, I could rearrange each parenthesis to be in the order x, y, z. I could do that, but aside from that, they're still not the same. I have 13x in one and minus 32x in another. So this could mean maybe I didn't take out the right GCF, but if I double check, there isn't anything additional I could have taken out. So when your parentheses end up not being the same, that means the polynomial is prime. It cannot be factored. Okay, so I could rearrange it so I had 2 groups that had something in common, but overall, the grouping didn't actually work. Now that doesn't mean when you have to rearrange terms that it'll always end up being prime. C, I know we skipped it for now. C, we would have had to rearrange as well, but it was not prime. It would have actually worked out like B did. So I just wanted to show you when you had to rearrange and show you what it looks like if it's prime. So you're not thinking it can be factored. Okay, any further questions on D? Okay, so then the last two examples, I'm going to talk about what it says above example 3 when we actually do part B, because it applies to part B. But these are examples where you will use one method to factor, and then you will still have to use another method to fully factor it. So checking to see what could I still do to make sure this is factorable. So the example A, the first example, how many terms do we have? Or what method of factoring should we try first? For A, yes. Grouping, yes. We have 6 terms again. Now, let's see if we need to rearrange it. If you look at the first 3 terms the way it's written, do they have something in common? Yes, they do. Okay, so I'll leave it the way it is. What do the first 3 terms have in common? Y cubed. So if I factor that out of the first 3, I'm left with x squared minus 3x plus 2. And then what about the last 3 terms? Z cubed. Do I want to take out a positive or negative? Positive. And then I'm left with x squared minus 3x plus 2. Okay, so grouping works here. My 2 parentheses are the same. So I can write this. One factor is x squared minus 3x plus 2. The other is y cubed plus z cubed. Okay, but here's where I don't want you to stop, because this can be factored more. So when I look at my first factor, the x squared minus 3x plus 2, hopefully this resembles chapter 4 to you. It's a trinomial, ax squared plus bx plus c. You should see if you can factor this using the diamond. Okay, if we're using the diamond for that one, what are we multiplying to for this trinomial? 2 and adding to negative 3, are there 2 numbers that work? Negative 2 and negative 1. And since the a value in front of the x squared is 1, I can go straight to my 2 factors. So this trinomial factors to be x minus 2 times x minus 1. Okay, so that's just from the trinomial. I factored it further. Now both of these factors, because it's just x to the first, these are done. So I can't factor those any further. Okay, now for the y cubed plus z cubed, either this gets brought down and it's still part of my answer the way it is, or it could be factored further itself. Anything stick out to you about y cubed plus z cubed? They're both cubes, so this is a sum of cubes, meaning it can be factored further, just like we did on the front. So your formula for the sum of cubes is on the front. It's what we just did in the first 3 examples. So the cube root of y cubed is y. Cube root of z cubed is z. And your formula, like I said, is on the front. So I'm going to write this. It's all going to be one answer. So I'm just going to continue on where I left off with the x minus 2, x minus 1. So this factors to be, first factor is a plus b. So it's y plus z times a squared, so y squared, minus ab, so yz, plus b squared, which is z squared. And that's the factored form of the sum of cubes. And so again, when you use a sum or difference of cubes, even though one of your factors is a trinomial, you cannot factor it any further. So once you use a sum of cubes or a difference of cubes, that is automatically done. So this whole thing, all 4 factors together, that is your final answer for A. That is the factored answer. Okay, questions on A? Just being able to recognize this and then practice it. So then part B, this one's a little different, and I'm going to read above. When you have a difference of 2 terms with exponents of 6 or higher, why this is a special case is when you have an exponent of 6, 6 can be divided by 2, so they are perfect squares. 6 can also be divided by 3, so they are also perfect cubes. So when it's both, like this is a difference of squares and a difference of cubes, since 64 is also a perfect square and a perfect cube, you want to factor perfect squares first before you factor perfect cubes. So I'm going to factor this as a difference of squares versus a difference of cubes. Okay, so your difference of squares formula is also in that box on the front. You find the square root of each. So square root of 64 I know is 8. To find the square root of x to the 6th, you divide the exponent by 2, so it'd be x cubed. And then the square root of y to the 6th is y cubed. So difference of squares, that's your a plus b times a minus b. Again, it's on the front of your sheet. So this would be 8x cubed plus y cubed times 8x cubed minus y cubed. Okay, that's the difference of squares. But then 8x cubed and y cubed are both perfect cubes. So here you have a sum of cubes and a difference of cubes. So both of these can be factored further using the formulas on the front as well. So I'm going to factor the sum of cubes first. They're going to look very similar. So the cube root of 8x cubed is 2x. Cube root of y cubed is y. So for a sum of cubes, it starts out with a plus b, so 2x plus y times a squared, and again that's 2x quantity squared, so it'd be 4x squared, minus a times b, so 2x times y, or 2xy, plus b squared, which is y squared. So this is just the sum of cubes. And then we also need to factor the difference of cubes. The nice thing is it basically looks the same, just the signs are different because the cube roots are the same, 2x and y. So with a difference of cubes, the first factor is a minus b, so it's 2x minus y. And then it's a squared, and again that's going to be 4x squared, plus ab, so plus 2xy plus y squared. And that's the difference of cubes part. So yes, the factored form, depending on what you have, especially when you start having more than 2 factors in your answer, can be long. But trying out the different methods.